If you have been tracking the OpenWeight's AI ecosystem lately, you know that finding a single model that natively handles massive context, complex reasoning, and deep visual understanding simultaneously has been nearly impossible. Most open models sacrifice long context retrieval for raw coding logic, or vice versa. That frontier bottleneck just broke. MiniMax has dropped M3, the first OpenWeight model to natively combine three critical frontier capabilities: elite coding and agentic performance, a massive 1 million token context window, and native multimodality built from step zero instead of being tacked on as a superficial layer. Today, we are going to bypass the marketing fluff, hook the MiniMax M3 API directly into our local development environment using Cursor, and spend the bulk of this video building a production-ready automation framework from scratch. Let us look at the hard data because the engineering benchmarks speak for themselves. On SWE-Bench Pro, M3 hits an impressive 59.0%. It scores 66.0% on Terminal Bench 2.1, 34.8% on SWE efficiency, and 74.2% on MCP Atlas. If you look at BrowseComp, it hits 83.5, completely outperforming close rivals like Claude Opus, which sits at 79.3. What makes this genuinely insane is how it handles long horizon agent execution. MiniMax ran an independent experiment where they tasked M3 with reproducing an ICLR 2025 outstanding paper called Learning Dynamics of LLM Fine-Tuning. The model ran continuously for nearly 12 hours, autonomously pushing 18 commits and generating 23 experimental figures to successfully replicate the core findings. Before we jump into the IDE, we need to understand why this model can handle a 1 million token context window with a guaranteed minimum of 512,000 tokens without absolute latency collapse. It comes down to their proprietary MiniMax Sparse Attention architecture, or MSA. Traditional transformers scale quadratically with context length, making a million tokens completely unusable due to compute costs and high latency. The MSA architecture splits processing into two distinct paths: an index branch that utilizes grouped query attention with block max pooling and top K selection, and a sparse branch that isolates attention to explicitly selected blocks. This hybrid gating mechanism allows M3 to process massive repositories, complex agentic workflows, and intensive visual components while maintaining fast token throughput and low inference latency. The entire pre-training data pipeline was rebuilt to scale past 100 trillion tokens, meaning text and vision are deeply aligned from the very first epoch. Now let us configure Cursor to route all of our LLM and agentic engineering requests through the MiniMax endpoint. Because MiniMax provides fully OpenAI compatible endpoints, configuring your modern IDE tools is incredibly straightforward. Open up your Cursor settings by clicking the gear icon in the top right corner. Navigate to the Models tab. First, we want to disable the default models to ensure we are explicitly utilizing M3. Scroll down to the OpenAI API key section or the custom OpenAI compatible model override area. You will input the following configurations. First, set your base URL endpoint to api.minimax.io/v1 for international routing. Second, paste your secret MiniMax API key generated from your developer dashboard. Third, add a new custom model name string exactly as MiniMax-M3. If you are using terminal native coding frameworks like Anthropic Claude Code instead of Cursor, you can achieve the exact same routine by editing your local settings.json file. You will just need to clear out any conflicting native environment variables like Anthropic_auth_token and point your base URL to api.minimax.io/anthropic, matching the model target field to MiniMax-M3. Let us put this frontier coding capability to work for a deep dive technical build. I have a local repository here for a decentralized tracking application. We need to write an automated script that parses incoming block transactions, decodes the raw smart contract event logs, flattens the nested JSON objects into a structured schema, and then flags anomaly variances higher than 2 standard deviations. I am opening up Cursor Composer and bringing the entire local context into play. I will prompt M3. Write a robust TypeScript automation script using ethers.js that listens to a specific contract address, processes log events asynchronously, applies standard deviation filters to detect anomalous volume spikes, and exports the data cleanly to a local database environment. Watch how quickly the context resolves. Because M3 possesses autonomous task decomposition, it does not just write a generic script. It outlines the modular components, accurately structures the async event loops, handles WebSocket reconnection states, and accurately maps out the mathematical logic for the standard deviation algorithm. Let us break down the code it just generated step by step. Notice how it creates a clean event listener interface using the Ethers provider block filter. Instead of nesting callbacks, which could lead to memory leaks over a massive token runtime, M3 implements a back pressure-aware asynchronous queue mechanism. This ensures that if the blockchain experiences a massive burst of transaction blocks, our local process will not drop events. Look closely at the statistical anomaly detection engine it wrote. It initializes an array to hold a rolling window of recent transaction volumes. It then calculates the moving mean and uses a highly optimized streaming variance algorithm to compute the running standard deviation. When a new block event arrives, it evaluates the volume against the threshold before writing to the database. It even pre-configured the environment variables and error handling infrastructure for database reconnection policies. Let us run the script directly inside the integrated terminal. The execution compiles flawlessly on the first try. 0 syntax errors, 0 hallucinated methods. The structural logic holds up perfectly under local environment testing. We can stream mock transactions into our listener, and the terminal instantly starts logging the past event parameters while cleanly filtering out normal traffic and triggering alerts on the simulated volume spikes. Having an open weight model perform at this caliber across long horizon coding tasks completely changes the cost efficiency math for independent developers and enterprise teams alike. To run these kinds of production agent workflows sustainably, you need an affordable infrastructure foundation, which brings us to the MiniMax token plan. MiniMax has simplified their billing by moving away from segregated models and unifying everything into 3 ultra-affordable tiers, where text, image, speech, and music all pull from a single pool. The Plus tier is $20 a month for roughly 1.7 billion tokens. The Max tier is $50 a month for roughly 5.1 billion tokens. The Ultra tier is $120 a month for roughly 12.5 billion tokens. This is highly competitive compared to standard market quotas globally at these price points. All plan subscribers receive full access to the entire MiniMax model family, including text generation, image creation, high-fidelity speech synthesis, and music generation models. If you are a developer looking to get your API access configured, you'll need to provide your group ID or GID to manage your membership. Simply log into platform.minimax.io, navigate over to the user center, and click on General. Your unique group ID string is right there on the main dashboard. Copy that, subscribe to the plan, and you are good to go. Even better, if you use the link in my description right now, you can get an exclusive 12% discount across all token plan tiers. The official links to the MiniMax platform, the subscription token plan, and the complete technical API documentation are pinned in the comment section below and listed right at the top of the description box. If you found this integration tutorial valuable, hit that subscribe button, drop a comment letting me know what complex agent workflows you plan to build with M3, and I will see you in the next deep dive. Happy coding!